Here we have a closed rigid tank fitted with a fine wire electrical resistor, and it's filled with refrigerant 22. R22 is the abbreviation. And we're told the initial temperature is minus 10 degrees Celsius and a quality of 80%, and volume, the container volume is 0.01 cubic meters. There's a 12-volt battery providing a 5 amp current to the resistor for 5 minutes. If the final temperature of the refrigerant is 40 degrees C, determine the heat transfer from the refrigerant. So we're trying to find the heat transfer, which makes me think that this is going to be a first law analysis, and we're going to apply the first law to the refrigerant, since that's what we're trying to find the heat transfer from. So let's go ahead and draw a control volume that surrounds the refrigerant. I'm going to actually include the resistor in there as well. I'm going to assume that the resistor mass is very small compared to the refrigerant mass. And let me write out the first law. This is a system, so the change in total energy of the system is equal to the heat going into the system minus the work done by the system on the surroundings. Now let's, actually I'm going to write this as the work done on the system. And the reason I'm doing that is because I know there's a battery here and it's doing some electrical work on the system. It's doing it through the resistor. So I'm just going to draw this as work coming into the system like that. So that's why I'm writing it as plus on the system rather than minus by the system. Okay, so let's go ahead and expand this out, the change in total energy of the system. That'll be equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy of the system. The kinetic energy and potential energy of the system aren't changing. The refrigerant R22 isn't moving around. It's not changing velocity. It's not changing elevation. So these two terms are zero. And so if I rearrange this, I'll have Q into is equal to the change in internal energy of the system minus the work done on the system. Okay. The change in internal energy of the system I'm going to write as the mass of the system. I'm just going to write it as M. I'm going to drop the subscript SYS just for convenience. It's going to be the mass times the final state, that's the final specific internal energy of the system, minus the initial specific internal energy of the system. The work done on the system is electrical work, and we're told that we have a 12-volt battery providing 5 amps of current, so the power associated with that, assuming that the voltage and current are constant, will just be the voltage times the current. That's the power, and it's operating for 5 minutes, so I'm going to just write that as delta T. So the voltage here is 12 volts, the current is 5 amps, and the time is 5 minutes. There's some unit conversions you'd have to do to convert that over to like kilojoules, for example. Okay, so what we're left to find now is the mass of the system and the initial and final specific internal energies. So let's start with the initial specific internal energy. We're told that we're dealing with R22, and the initial temperature, let me write these down. So R22, T1 is minus 10 degrees Celsius. I'm also told the quality initially is 80%, so 0.8, and the volume of that container is 0.01 cubic meters. Since we're dealing with a quality, we know that we have a saturated liquid vapor mixture phase, and we should be able then to determine the specific internal energy using the quality in the following way. So U1 would be 1 minus the quality initially times the specific internal energy of the saturated liquid initially plus the quality times the specific internal energy of the saturated vapor initially. And to find these two terms, we'll use the saturated liquid vapor mixture table for R22, organized based on temperature, since I'm given a nice round temperature here of minus 10 degrees C. So I've copied the tables from the Moran textbook, and let me just show you that in a moment. Okay, here we are. So this is the saturated liquid vapor mixture table for R22 from the Moran 8th edition textbook. And we have a temperature of minus 10 degrees Celsius, so that puts us right here. And the specific volume, I'll just go ahead and note those. We're going to use that information in a moment. Those are the specific volumes, and here's the specific internal energies. This is what I'm most interested in at the moment. So here's the saturated liquid specific internal energy and the saturated vapor specific internal energy. So let's try to remember those numbers, and we'll come back up here and do the calculation. So this one is, that was the 33.27 kilojoules per kilogram from the table, and this one is 223.02 kilojoules per kilogram. So when you plug in those numbers, you'll get that U1 comes out to be 185.07 kilojoules per kilogram. All right, so we have one part of this. While we're at it, since I'm given, so we have to find the mass here, and since I'm given the volume, if I know the specific volume, I should be able to find the mass, right? So remember that specific volume is the volume divided by the mass. So I could rearrange that to find the mass is the volume divided by the specific volume. So if I can find the specific volume at state 1, then I should be able to find the mass. So I can find the specific volume in the same way that I found the specific internal energy. So I'm just using the quality here. So this is the so this is the fraction of mass that is a liquid, and this is the specific volume for the saturated liquid. Here's the fraction of mass that's vapor, and here's the specific volume of the saturated vapor. So again, I can use the tables. Let me go back down here. Here's the saturated liquid specific volume. Notice that this number has been multiplied by 1,000. So you have to multiply this times 10 to the minus 3 to get the actual specific volume. And then here's the specific volume for the saturated vapor. So let's remember those numbers. So this one is it's 0.7606 times 10 to the minus 3 cubic meters per kilogram. And this one is 0.0652 cubic meters per kilogram. So then the specific volume in the initial state is 0.0523 cubic meters per kilogram. And now that I have that, I can go back up to this expression. Since I know the volume and I know the specific volume, I can find the mass. And so you get that the mass will come out to be 0.191 kilograms. Okay, so we're making some good progress here. So now we know the work done on the system. We have the specific internal energy initially. We have the mass. Now we just need to find the final specific internal energy. Okay, so to find the specific internal energy in the final state, we're told that the final temperature is 40 degrees C. So let me write that down. So T2 is 40 degrees C. We need another piece of information to nail down what the properties are in the final state. And so the other piece of information is that we're dealing with a closed rigid tank. Okay, so it's important information. Since it's closed, we know the mass in here remains constant. Okay, I guess I sort of assumed that when I wrote this down, was that the mass was the same at state 2 as well as at state 1. If it wasn't, by the way, if it wasn't the same, then it would look like this, M2U2 minus M1U1. But it is the same, so we know that M2 is M1 is just M in this particular case. So the closed means the mass is the same. The rigid means the volume remains the same. So the volume at state 2 is still this volume. Since it's closed, we know it's the same mass. So we know then that the specific volume should remain the same, right? If the volume and the mass are the same, then the specific volume has to be the same. So the specific volume at 2 will be the same as the specific volume at 1 because it's a closed rigid tank. So that means that our specific volume at 2 is 0.523 cubic meters per kilogram. So now I have that second piece of information, and I can go back to the tables and see what kind of phase we're in and find the other properties. So let's see, 40 degrees C, 0.0523. Let's go down to this table, again, organized based on temperature. We're at 40 degrees C. And remember, our specific volume at state 2 was 0.0523. Okay, just as a note. So now when I come here, remember it's this set of columns here that is the specific volume. So when I look at this, remember this one is multiplied times 10 to the minus 3 for the saturated liquid case. So it's clearly my specific volume is bigger than that. And in fact, it's even bigger than the saturated vapor one, right? So if the specific volume is greater than the saturated vapor specific volume, that means I'm occupying more volume than the saturated vapor, which means that I would be in a superheated vapor state or phase. Okay, so I'm not dealing with the saturated liquid vapor mixture any longer. I'm actually dealing with a superheated vapor. So then I go to the superheated vapor table for R22, again coming from the Wiley textbook. And we're dealing with 40 degrees C. Okay, just remember T2 is 40 degrees C, and V2 was the 0.05, what was it, 0.523 cubic meters per kilogram. So I look here at all the different 40 degrees. So here's 40 degrees, and in this column, the column we're interested in is this first one. It's a little hard to see here, but that's the specific volume column here. So what I'm looking for is at 40 degrees, like here it's 0.08224, so that's too large of a specific volume. And then as I increase pressure, notice here that the pressure goes from 3.5 bar to 4 bar. As I increase pressure, you can see this specific volume is getting a little bit smaller, so it's still too large for what we have. Here's 40 degrees C. We're getting closer. That's still too large. Here we are at 5 bar. This one's getting pretty close, 0.05636. So we're just a little bit lower than that particular specific volume. And then here we are at 5.5 bar. And this one is less. Remember, our specific volume is 0.0523. And here it's 0.05086. So we're somewhere between that specific volume and this specific volume. Let me just kind of highlight 40. So we're somewhere between those, right? So our specific internal energy will be somewhere between 250.7 and 250.2. Okay, so we're somewhere in between those. So in order to find those, we're going to have to do some linear interpolation between them. Okay, hopefully that makes sense to you. The way we linearly interpolate, so U2 would be the lower specific internal energy here. Is that the right one? 250. No, I'm sorry. It'd be the lower one right here. It's just whichever one you want to start with. I'll use the lower one. 250.2 kilojoules per kilogram plus the slope here. This would be 250.2 minus 250.7 divided by the specific volume difference. So this one would be 0.05086. It's the specific volume down here corresponding to 250.2 minus this one up here, which corresponds to the 250.7. 0.05636 cubic meters per kilogram. This is kilojoules per kilogram. So that's the slope. And then my actual specific volume, I'll just write it as V2, it's this one right here, minus the one corresponding to this one right here, the one corresponding to the 250.2. Okay, so anyway, it's kind of tedious, but you can work that out, and you'll find that the specific internal energy at 2 is 250.33 kilojoules per kilogram. Okay, so we can mark that up here. So this is superheated vapor phase, and we can find that U2 is 250.33 kilojoules per kilogram. That comes from linear interpolation of table values. Okay, hopefully you understood how we got those values. So now I have everything I need to calculate the Q into. So if you plug the numbers in, you'll get that Q into comes out to be 5. Let's see. Let me clean that up a bit. The Q into comes out to be minus 5.54 kilojoules. Let me just double check that I got the numbers correct. Yeah, that looks correct. So there's actually, since it's negative, it means that there's heat transfer out of this container. So, you know, I should have drawn this at the very beginning. We're trying to find the heat transfer. I assume that the Q into is going into it, but it's actually coming out. So it's 5.54 kilojoules of energy leaving our R22. Okay. So this was just an application of the first law applied to this control volume. I assume that the resistor mass was negligible, so when I did this calculation here of the change in internal energy, I only factored in the mass of the refrigerant. So it was and then to find the work, we knew it was electrical work. And then to find the specific internal energies was a matter of using the tables and the quality. And then at state 2, a key piece of information was knowing that we were dealing with a closed, rigid container. Closed meaning the mass remains the same, rigid meaning the volume remains the same. So that means the specific volumes remain the same between state 2 and state 1. Again, we went back to the tables, found that we were dealing with a superheated vapor phase, did some linear interpolation to get the final specific internal energy, and then we found that there's actually energy transfer out of the R22 to the tune of 5.54 kilojoules. One last thing I'm going to do is let me just sketch this process on a TV diagram. And so here's our vapor dome, and we're dealing with an initial, I think our initial pressure, I guess it wasn't given, but we could find it actually, the initial pressure, since it's in a saturated liquid vapor mixture phase, the initial pressure is right here. It's the saturation pressure at minus 10 degrees C. It's the 3.55 bar. So the iso bar looks like this. So we're at minus 10 degrees C, and this pressure is 3.55. I'll just approximate it there, or just round it. And we're somewhere under this vapor dome here, and there's state 1, because I know it's in a saturated liquid vapor mixture phase, so I'm down here. And then state 2 is at a temperature of 40 degrees C. And I'm in a superheated vapor phase for that one. And remember, the specific volume remains constant. So state 2 is like right there. So I just went like this, because specific volume at state 2 is the same as the specific volume at state 1. So I just went vertically upward. And if we wanted to find what the pressure was corresponding to that, we'd have to do the interpolation, which I'm not going to do. But the pressure for that point is somewhere between 5 bar and 5.5 bar. So if I was to draw the isobar for that one, it would look something like this, where this pressure is somewhere between 5 and 5.5 bar. I'd have to do the linear interpolation to figure it out, but it's somewhere in there. And Okay, I think that's everything we need to do for this problem, so I think I'll go ahead and end the example there.